To build a bridge, lay a highway, or dig a tunnel, engineers have to first solve a specific physical problem, translating the messy, uneven terrain of the real world into an accurate mathematical grid. For centuries, the solution to that problem was the optical theodolite. This brass instrument was the surveying workhorse of the 18th and 19th centuries, used to map the entire British Ordnance Survey and chart the expansion of early railway networks. A theodolite performs one primary task. It measures the horizontal and vertical angles between designated visible points in the distance with precision down to seconds of arc. Mastering those exact angular measurements gave civil engineers the coordinates they needed to define property lines, align heavy infrastructure, and push railroad tracks across entire continents. Using one of these analog instruments in the field was a manual process. A surveyor relied entirely on human eyesight and physical adjustments to capture a single data point. Setting up the instrument required centering it over a specific mark on the ground using a gravity-driven plumb bob. Then, the surveyor turned foot screws until a plate bubble rested perfectly in the center of its glass vial. To read angles, they used a vernier scale, aligning tiny overlapping marks on a metal arc by eye to calculate fractions of a degree. These early theodolites could calculate exactly what direction a target was, but not how far away it was. Surveyors had to stretch physical steel tapes or drag heavy measuring chains across the terrain to find the distance separately. As the pace of construction accelerated in the 20th century, this analog workflow created a logistical bottleneck. Relying on the human eye to read tiny scales and transcribing data into physical notebooks slowed massive projects to a crawl. To increase efficiency, engineers began systematically replacing the theodolite's mechanical parts with microprocessors and digital sensors. First, they swapped the manual vernier scale for rotary encoders. These discs calculate the exact angle internally and output the result directly to an LCD screen, removing human reading errors from the process. Next, they replaced liquid spirit bubbles with electronic tilt compensators. These internal sensors automatically detect microscopic misalignments in the device's level and adjust the mathematical readings accordingly. The most significant addition was electronic distance measurement, or EDM. A single instrument could finally measure both angles and distances simultaneously. EDM works by firing an infrared wave or laser pulse from the telescope toward a target prism. A sensor measures the time it takes for that light to bounce back, instantly calculating the distance based on the speed of light. By combining digital angle encoders and EDM into one chassis, surveyors eliminated the need for separate manual tools, which allowed for much faster data collection in the field. In clear conditions on the surface, these digital sensors provide immediate readings. But deep under the earth, inside massive tunnel projects, surveyors face a unique environment where GPS signals cannot penetrate rock and there are no stars available to establish true north. To navigate these extreme conditions, engineers rely on a highly specialized electromechanical variation of the instrument called a gyrotheodolite. Inside the housing, a suspended gyroscope spins at 20,000 revolutions per minute. At this speed, the gyroscopic reaction to the Earth's daily rotation forces the spin axis to align with the plane of the meridian, pointing precisely at true north. During the construction of the Channel Tunnel, gyrotheodolites were used to guide boring machines from both France and the UK. The instruments maintained exact alignment deep beneath the ocean floor, ensuring the two sides met perfectly in the middle. By merging the physics of Earth rotation with surveying optics, these tools pushed human engineering capabilities into environments where standard orientation tools would fail. The continuous integration of these digital components produced the modern standard for civil engineering, the total station. A modern total station functions as an onboard field computer. It handles the processing and storage of thousands of individual data points directly on the hardware. For instance, the onboard microprocessor automatically applies atmospheric corrections. It measures ambient temperature and pressure in real time to adjust distance calculations, compensating for the way air density affects the return speed of the laser. The instrument instantly combines the measured angles and EDM distances to calculate exact three-dimensional coordinates for every single point it targets. At the end of a shift, surveyors no longer transcribe numbers by hand. They download thousands of coordinate points straight from the instrument's memory directly into CAD software. This evolution moved the surveyor's role from reading manual scales to managing high-volume digital datasets. This integration translates physical landscapes into CAD models at a speed that matches the rapid pace of modern commercial construction.